Okay, year 9. Last unit for the semester. And the good news is we'll be able to spend the last fortnight actually doing some physics, which will be good. But for the first bit, we'll do a little bit of theory to fill in those last 2 weeks of classes before we get back. So we're looking at forces, and we're looking at Newton's 3 laws of motion, which are all about forces, really. So we'll talk about what is a force, talk about the idea of balanced and unbalanced forces, the 2 critical forces, friction and gravity, and then we'll talk about the idea of Newton's 3 laws and inertia. So, what's a force? Well, the definition is it's a thing that changes the shape of an object, or its movement, or as in gets it moving or stops it moving, or changes the direction of its motion. So, pretty straightforward. Force causes that change of motion or that shape. When forces are balanced, an object is either basically not moving, or it's holding its normal shape. So there's all the forces working on it are in balance. And opposite. So you can see this guy standing here. He's got the force of gravity pulling him towards the center of the planet, and this anti-gravity, the floor, pushing him upwards. They're balanced out, and he's nice and stable. When forces are unbalanced, we can see that they're moving. Either the forces are one's greater than the other, or they're pulling in the same direction. So we now see a change in the motion or the shape of the object. So they're either unequal in size, or they're working toward the same direction, or they're not opposite to each other. So we see these unbalancing effects. And that's the classic seesaw allowing you to do that. Friction is a force that opposes motion, and it's always present. So we can use friction for our own purpose. That's how we go around corners in cars. And it allows us to control a vehicle on the road by creating friction between the tyres, the surface of the tyre and the surface of the road. Or it can be a problem, as this poor polar bear is finding, where he's knocking enough friction between his feet and the ice, and he's sliding away. So it's a force that tends to work against motion. And it's a force created between surfaces. And we often think of the feet of that polar bear and the ice. But of course, if the polar bear was swimming, that would be the water against his body. And when he's walking, he's still working against the atmosphere. So the air causes friction and opposes motion. You've got to overcome that as well. We don't tend to think of it that way, but that's still the case. Gravity is the other sort of common force that we're always experiencing. And we don't think too much about it because it's classic. It's 9.75 meters per second squared on around sea level on the planet. We don't really see any change in that, so we don't think about it too much because it's always there. We just don't have to react to it. But all objects have a gravitational force. The bigger and more massive an object, the bigger and more massive its gravitational force, and so more likely to have an impact. And obviously, if you're very small and there's not much of you at all, you're not really going to have much impact on others. But all objects that are sitting around you, I'm just staying here, sitting at my desk with a computer, and there's a lamp on, and lots of these objects around me are experiencing gravity towards each other. And some are bigger than others. And of course, the planet is overriding all of them by drawing us towards its centre. There's a pull towards the centre of the Earth. That's the important thing about gravity. And then, of course, if you want to work out the weight of something, then you need to work out the gravitational pull and multiply the mass by that gravitational pull to get a weight. So weight isn't a direct measurement of mass. It's a measurement of mass and gravity. And we'll look at that in the style lessons during the next couple of weeks. And then we've got Newton here, this lovely fella, and his 3 laws. And the first one's basically the law of inertia. This essentially says that an object will remain at rest or in a constant motion, so speed and direction, unless acted upon by a greater force. So you see this when you're in a lift. Oh, actually, lifts are probably not a good experience. Say you're in a train, and the train's hurtling along and stops. You want to keep moving, so you go forward as the train stops. As the train starts again, you go back because you're trying to stay where you were as an object. You see the car, the car goes around the corner, and you try to stay where you were, and the car's going that way, no, that way, and you swing around the back seat. Especially if the person driving is trying to wind you up. So inertia belongs in all objects, and again, the more massive an object, the more mass it has, the greater that inertia. Newton's second law is often described as F equals ma. So force equals always equivalent to the mass of the object multiplied by acceleration. And when we talk about acceleration, we're talking about the change in velocity, or speed in common language, but we're talking about velocity in physics. So the change in velocity multiplied by the mass, the number of grams or kilograms of the object, will give you a sense of how much force it has. So a 1,000 kilogram car accelerating from 0 to 100 kilometers per hour is going to have an immense force, and you don't want to get in front of it. That's Newton's second law. Newton's third law is one we're playing with at the start of the year, and we're playing with our rockets. And it's that idea: for every action, there's an equal and opposite reaction, or there's two forces at work, and they're equal and opposite. So if I create a force downward in my rocket, then the force in the opposite direction should be equal and opposite to it. So it should cause my launching. So I get enough force going down, then I'll get force of the object going up, which is what we'll try and do with our rockets. Of course, we had all that problem of burning sideways, and a few of them actually got to leap a little bit, but it's hard to make those work because it's, again, you've got to overcome the gravity of the object. So the more mass in the object, the greater gravity and inertia you've got to overcome before this rocket launches. We had a little bit of success, and we've got a chance to have some play with some rockets again when we get back to class and see if you can get these things to take off and how much force it requires. Anyway, that's sort of a quick introduction to our forces and the three laws. You're going to do some style lessons over the next 2 weeks and explore these in much greater detail. And then when we get back to class, we'll get to do some practical work and explore them hands-on, which will be a great way to finish the semester. Looking forward to seeing you in class soon.